and here we plot it, right? Here I am putting real because we will see that we can also do this with complex numbers and also get a solution. So we see that this is the exact solution in orange, and in blue we have Euler's method approximation for this particular delta t. If I want, I can change the delta t to be smaller, for example, from 0.15 to 0.1, and I run it again, and I will get something that is a bit closer. And each time I do this, I will get a closer solution to the real one. But we see that this method has some issues here where it undershoots the solution. It's not really getting there. This is because we are kind of missing the solution because we are using the derivative at a certain point to project where we want to go, but the function still grows in that interval. So we undershoot where we want to go, right? If you want, you can also try here putting some imaginary values, right? We just need to comment here. We'll use lambda imaginary, and we start with an imaginary value as well. And let's uncomment here. What we expect here now is to have a solution of the form the exponential of it, right? And this should be a circle or an ellipse depending on the value of lambda. And this is, for example, the exact solution. And this is our numerical approximation. So this is kind of not really pointing correctly the Euler method. If we choose a smaller delta t, then of course we will get closer to the real solution, but still we are kind of getting away. Let's do some more points so we can see an entire circumference, right? So the Euler method is not really very good, but at least the explicit Euler method, but it's a good starting point, right? So what we can do also is try to analyze the error that we are making in each step, right? So let's assume that up to a certain point, Euler method has worked perfectly and the solution is exact. And now I do a new step in time. Okay, how does the error, how is the dependence of the error that I have in the solution in the new time step with respect to the time step that I am using, right? So right now I am doing like some small Taylor expansion here, right? So I have the error at step n is equal to y at the step n, the exact solution, minus or w at n, right? And here I can do some Taylor expansion of the solution, the exact solution, based on the previous step, right? So this is an expansion of y in t-1, and here we have a Taylor expansion and also our little our time step here, also starting from the previous step, right? And here we are using this to assume that in the previous step that we made no mistake. So here, when we reorder this, we get the error in the previous step plus something that grows with delta t plus something else extra that goes with delta t squared, right? So if we assume that the error in the previous step was 0, then we will see that the error in the new step will be order delta t squared. That is, the next step, if I try to use a delta t half as long as I used before, then the error will be a quarter of what it was before. So let's not this may look like we are saying that this method is order delta t squared, but actually the problem is that we are actually making several iterations. So each iteration we are multiplying by delta t, and this global error is getting accumulated. So the actual error in our solution is order delta t, not delta t squared, right? So this is what we can see in this cell here. So what we are doing is trying several values of delta t and trying to see what our approximation is of y after t equals 1 is achieved, right? So we are evolving here, evolving until t equals 1 for several values of delta t. And this is what we are seeing. This is the error in the solution, and this is delta t. And we see that this is linear. So each time I make the delta t a bit smaller, the error is smaller, but it's linear dependence. And we would like methods that are a bit better than this, so that I don't have to use a very extremely small delta t to get a good solution, right? Now we will mention multi-step methods, because as you saw, what we did just now was just make a Taylor expansion. I say, okay, I have the solution at this time, I want the solution at the next time, I do a Taylor expansion, and I get a very simple method. We can try to play a bit more with this expansion and see if we can cancel out, for example, the linear term and get something that's order delta t cubed, delta t to the fourth, and so on and so forth, right? So this is what we are doing in this multi-step method, right? Here, what we are doing is taking y in the, 1 delta t to the future and 1 delta t to the past, and we are subtracting them. And this gives us this cancel out some terms in the Taylor expansion, and what we end up in the end is this algorithm, where what we are doing is, okay, if I want in the next time step in tn plus 1, then I need the information of the previous time step here, wn, and I also need wn minus 1. So it's kind of like I'm taking the previous step, I am using the derivative and the current step that I am on, and I am using this to project to the next step. And this will be, this will have a local error on that's third order, so the global error will be second order. And this is this only requires one single evaluation of f, so it may look like a good method, but when you look at it again, you realize that here we need 2 initial data, right? Well, in our original problem, we have a differential equation for y, and we have 1 point where we know the solution. So we actually need to try to guess 1 step to start making iterations, right? Because we also always need the previous step, and we don't know already the previous step of the first step. And if we make some mistake in that initial guess, we will see that we get some error that starts growing. So this method has instabilities, can produce poor solutions. So it's not really practical, but we will still try to implement it here. So in this case, I am again doing I am defining how a multi-step works, right? This is one single step, and I need the solution in the previous step, y previous, I need the current step. This is what I am returning here. And now here I am defining some delta t, some complex parameters, for example. Here I have set delta t equals 0.2, and I try to evaluate this. And what I see here is this, that I am kind of getting the circle that I wanted to get, but still I am kind of getting out of it. I am kind of out of it. And this is because the first approximation, the first step, what I did was a silly Euler step to try to get there. And I kind of get two series of solutions that the problem is actually oscillating around. For example, now I can try to do like some lambda, some real lambda here, and try to plot this, right? And again, we'll use certain points, and here let's put, for example, delta t equals 0.1, right? And we see the solution here, and we see that this multi-step method maybe it starts okay, but then it's like we have two solutions that we are growing, and one of them will start to grow, and suddenly our method is not working anymore. But okay, maybe this is still going somewhere. Maybe we can try to work out how to solve this problem. Again, this is just the error in a case where this is working. This will be no longer linear but quadratic. The error in y. The third idea that we are going to explore, and this will actually get us somewhere better, is to do a single step method, right? So what we are trying to do in this case is say, okay, let's assume that I do some small Euler step, right? So I will try to show it with this graph here that I have item here, right? So imagine that I am in this point here. This is the certain value of y, right? And this arrow here is telling me where I actually want to, where I am actually going, right? This was the f of y. This is where I am pointing at. So what I try to do is, okay, let's imagine that I go this distance and I stand here, and I now calculate the f at this point. This will give me a new value of f, a new approximation of the derivative, and then I use this value of f to actually go to the next point in the iteration. So this is what's happening here, right? What I do is I define some k1, right? That is equal to delta t times f on the point where I am at. And then I say, okay, let's calculate k2. That will be f applied to the midpoint of the way there I was going to the midpoint to where I was pointing at with the first k1. I don't know if this if you are following me here, but with this new approximation, right, I can get this new scheme, right, that does not require two previous steps to compute, only one, right? And I just do some manipulations on how I apply f, and this is what I am trying to show you here, right? This is called the midpoint method, or the improved Euler method. This is what I am trying to plot here, and this method actually seems pretty reasonable. Like, we are actually, this method is stable, does not have the same issue that we had before. Here we can see the implementation, right? And we can also check the error that we have on this method and it's also quadratic, right? It's cubic locally, but globally it is quadratic. Again, we can try here to see some solution that is imaginary. And try to see where we end up. And here we will uncomment here, so we can plot. And now we are much closer to the circle than we were before. Okay. So again, this is an explanation of how the method works. We start at a certain point, right? And we want to continue here, right? So we actually point somewhere. We go to this point, and then we try to evaluate f on the midway there to get a new approximation of the derivative, of new approximation of f, and then we use that value to press forward, right? We could also have done this another way. For example, we could have done a full step ahead, right? Here in this case, we start with an Euler step, and then at that point we again approximate what the step would have been if the f had been the one in K1, right? So if we had gone all the way there, we have a new value of f. Then okay, if we had taken that f, what would the Euler step have given us? And then we average the two solutions. This is Holmes' method, and this also has a local error of order dt cube. You can always check this by checking the derivatives and seeing what cancel up with who, with what. And actually we can do it in a more general way, just defining, okay, instead of doing this, we will do this step here, where we have defined some constant alpha and some two other constants a1 and a2 to try to get to the next step. And we do some Taylor expansion, and we can see several values of alpha, a and a1 and a2, and see what order the methods end up being, right? In general, it will be linear, for example, if you are not careful with what you do, but if you are careful, you can cancel out some terms, right? So for example, the midpoint method, the first method that we saw, would be exactly this, but using alpha equals 1/2, a1 equals 0, and a2 equals 1. And Helm's method is with alpha equals 1, a1 equals 1/2, a2 equals 1/2, right? So this method here is the same as here, but using these values of alpha, a1, and a2. Okay. Right? Okay. And these are what are known also as Runge-Kutta methods, right? So Runge-Kutta methods, what actually do is this kind of dance with the solution, where you start at your value and you kind of point forward where you want to go, then you go to the midpoint there, and then you apply f again, and you do that a couple of times just to trick the derivatives and get each time a smaller error, right? For example, here what we have is the Runge-Kutta fourth order, right? That is very useful. I'm sorry, here there is a t that should be removed. I will add it later. Okay. And also a p. There it goes, right? So this is a Runge-Kutta fourth order method. So doing this trick here, we get a method that is much better than any of the methods that we had before. And I encourage you, if you want, to just take the code of any of the previous methods, right? For example, I don't know, this one here, and try to rewrite this to get to Runge-Kutta 4 method, and try to see if you can replicate the error. So just that you can play something with Julia. Okay. Okay. Let me check. Okay, are you still following me? Yeah, when I'm saying linear, I was referring to first order. Yeah. Okay. So, of course, we can extend this to systems of equations. Right now, we are using just a single equation. Y is just a scalar quantity, but y could also be a vector, and this will be very useful later on when we go to partial differential equations. We understand y more as a full vector, right? So to do this, we can start with the harmonic oscillator to understand a bit about the systems of equations, right? So the harmonic oscillator appears a lot in physics. This equation, right? This equation is what governs for example, the movement of a spring or maybe a pendulum and the oscillations, and also, I don't know, physicists love to use the harmonic oscillator, sometimes where it doesn't belong, but the thing is, it's a very easy equation to solve, right? For these equations, we actually need two initial conditions. We need the initial value of x and also the initial value of the derivative of x with respect to t. And we will have a solution that is essentially a combination of sines and cosines, right? If we derive these two times, we will get this equation here, right? With this initial condition. So when we see this at first glance, it looks like this has nothing to do with what we were doing before, because here we have a second derivative in time, not a first derivative in time. But we can also convert this to a system of equation, right? Just by defining the velocity t equals to the derivative of x with respect to time, right? So if we do this trick, then we have that the derivative of x with respect to time is equal to the velocity, and the derivative of the velocity with respect to time is equal to minus k times x, right? So this equation here. So the derivative of the velocity is the acceleration. So now we can consider y, the t, is equal to the first component, a vector whose first component is the position and the second component is the velocity. And f of y is actually just multiplied by this matrix here, minus k1, right? And this is the system that we want to solve, right? And to solve this, we will use the differential equations package, so we don't have to continue to define all our methods. I hope it runs this time, because this is the first time it was installed this computer, and it took a while, a bit before. But as this, okay, it ran. So what we are doing here is defining the problem here. We are defining oscillator here, and this is how our differential equations likes to see the function, right? So here we will have a du that is actually an approximation of the derivative, that is this side, the dx over dt and dv over dt, which will be a vector of two components, u, the solution at the current step, the parameters that we want to solve the equation, and the time t here. So here k, for example, will be the only parameter that we are using, and use that the derivative of the first component is equal to the second component here. The derivative of x is equal to b, and the derivative of the second component is minus k times u. Here, this is this equation here. The derivative of b is equal to the derivative of x is equal to x times minus k. And here we have our exact solution again. We give some initial conditions, so we start at x equals 1 and velocity equals 0 and see where that gets us. Right? So this is just a definition of the parameters. And here is the fun part. Okay? So, this package, to use it, what we will first have to do is to define the problem. So here we are using this problem here, and we are storing this in this variable called prop. And this problem consists of the equation that I want to solve. This will be the f. Here the initial data that I have, in this case will be a vector. The values of t that I want to solve in here. This is the span of t. This is actually an interval. And these are any parameters that I need to make oscillator work. Okay? And then I simply call solve here with the problem that I just defined, the method that I want to use, and certain time step. And here we can also, I got confused and I used it here. This will always try to do the method adaptive, so we will change the value of delta t as long as it needs, but we can change that by adding this line here, adding false. Okay. And here I am using the Numerical method, and I am plotting both the solution that I expect as a function of x and y, which would be a circle, and then the real solution and the exact solution and our approximation here of x over time. And we'll see that the Numerical method is very good. If I wanted, I could have chosen here to use the Euler method that we defined before. For example, here, I uncomment here, uncomment here, and again I run, and I get what we had before, right? This will be Euler's approximation, pretty bad. I left you there a couple of other methods that you can try. For example, you can try the midpoint method that we implemented before. Solve it here. We see that we start getting some slight error in the face after some time, or whatever method you want to use. Here I put some methods to check, some of the ones that we implemented before, but you can also check the documentation. There are lots of methods of even higher order than Numerical, maybe 5th order, 6th order, stuff like that. Some of them are optimized to certain kind of problem, that is problems with certain kinds of functions f that may make the solution more difficult to attain. So right now we leave it at Numerical again. And let's try to see some geometric interpretation of what's going on. Just ignore the code. Here what I am interested in is actually the graphic of what we are seeing here. So in this direction, imagine that we have x, and in this other dimension what we have is y. And each arrow represents where the value of f, right? So f of y will also be a vector, and it will be pointing somewhere, right? So when I say that the derivative of y with respect to t equals f, what I am actually saying is, imagine that we have this space here, and I am at a certain point in this phase space. So the arrows tells me where the solution is evolving to, right? So this circle here, for example, which is a solution, is actually tangent to all of these arrows in this vector space. Okay, so all the methods that are doing what the methods are doing here is trying to see the arrows here and try to find how to point and how to navigate between them to get as close as possible to the solution. Other method has the problem here that imagine that I start here. Okay, the arrow actually points a bit outward from the circle. So it points, gets there, it points again, gets there, gets there, gets there, gets there, and actually starts doing a spiral. If I take delta t a bit smaller, then I will not get as far away from the circle as before, but I will always get away from the circle. Other methods try to do, what other methods try to do is, okay, I point here, I get here. Ah, okay, and what's the arrow at that point? This is the arrow at that point. Ah, okay, so maybe if I use the arrow at that point, combine it with the arrow that I had at the beginning, I can get something better of smaller order, right? So this is the observation that we have here. The solutions that we have are actually tangents, are curves that are tangent to this field, and the methods that we have are always trying to navigate this field here, right? If you see this, maybe the midpoint method or Runge-Kutta method will be easier to visualize, to understand at least the idea of what's going on, right? This is another example. This would be the equation for derivative of y with respect to t equals lambda times y for lambda real, right? So these are different initial values, where this gives us the solution for different initial values here, right? And this is f. In this direction we have the time here, and in this direction we have y. And this is actually the vector field that we saw before, and these are actually the solutions, right? In this case, imagine again that we have a system of equations and that t is another variable with derivative equal to 1. So t always goes forward in time. I'm saying this to reconcile with this graph here that does not have time. You can imagine time being here as an extra variable, and that this would actually be a spiral, not a circle in this image. Okay. To now, I want to know if you are following me here up until now. Okay. See no problems up until now. The last thing I wanted to mention was what I told you before in the first step, that we were only working with autonomous systems where the time dependence is not explicit on f, and we can write it here. Okay, let's try to see what happens if f also depends on time. But it's actually very, very easy to solve. We just need to consider time as a new variable. Imagine that there is a new variable lambda that is linear in time. So the derivative of lambda with respect to time is equal to 1. And then here I solve this system with, instead of putting t here, I put lambda. And I evolve this system here. This system is equivalent to the one that I show here. So I just added a new variable and I am evolving that variable here. And I will get exactly the same as if I had solved this system here. So in general, when you have these methods here, the ones that we had before, you can also add t as a new variable, and a new k1 and a k2 and so on and so forth. And this will give you a new value of a new way of how to do the method, just to consider the t value, for example. Here, for example, I left as an exercise. You can actually follow this equation here and try to see that this would be, for example, the Runge-Kutta 4 method. So you take the Runge-Kutta method that I showed you before and try to say, okay, there is a new variable t, and add it here in the method for f, and this will be the adaptation of that method here, right? So we have also time here in this Runge-Kutta definition, and This is how the time dependency is considered in the evolution. Okay, so basically this is what I wanted to talk to you about. I recommend you see this notebook, you read it carefully if you want to, and try to play a bit with the solutions. Try to see what happens if you change delta t, what happens if you change the value of lambda. You can also try putting other values of f that you want to solve. Like I want to solve, for example, for f being the sine of y instead of being lambda times y. You see what you get, and so on and so forth. Yeah. It's in the GitHub, PDE. Yeah, in the PDE GitHub. It's in lab 1. You should see it. In lab 1, you should have the one with the logistic equation that we saw before, and this one, and this notebook here about partial differential equations, about ordinary differential equations, right? These methods, of course, are called, when we talk about Runge-Kutta, we talk about it as an integrator, because what we are actually doing here is integrating in time, right? We have a solution, and we have the derivative of y over t, and we want to make an integration to get the full y. So, any questions, any doubts, anything you want me to go over again? Okay. Here, any questions? Okay, all good for now. Okay, so we'll meet again on Monday at 9 a.m. Brazil time and Buenos Aires time too. So until next time, please remember to do homeworks 1 and 2. You have until the other Friday, and feel free to ask any questions you need about them. Okay? Thank you very much.